So it is a great pleasure to have with us today Dr. Evangelia Tremou. Dr. Tremou got her undergraduate degree from the Aristotle University of Thessaloniki, like so many of us, and her PhD from the University of Cologne in Germany. She did her PhD studies at the IMPRS joint program between the University of Cologne, Bonn, and the Max Planck Institute for Radio Astronomy. And then she, for her postdoctoral research, she has traveled the world. So she has worked at the Yonsei University in South Korea, at Michigan State University in the United States, at Saclay in France, and now she's talking to us from or nearby, due to COVID, the Observatoire de Paris. Today she will talk to us about the transient sky through the radio window, and without any further ado, Lilia, the floor is yours.
Thank you very much. Thank you, Vaso. Thank you all for having me here. Let me, before I start, I guess, to stop my video to make sure that the connection goes well. I will switch it on again back for the questions later. So yes, thank you very much for giving me this opportunity to share my scientific interests with you. Although this is a virtual seminar, I'll try to be as interactive as possible. And please, even if after this session, if you have questions, don't hesitate to drop me a line in my mail here. I'm always happy to discuss about those things. Okay, so yes, as Vaso said, today we're going to talk about, and if you had the chance to go through the small paragraph I've sent for the abstract, you may have realized that today we're going to talk about exploring the radio window, the radio observations, and what kind of exciting things we can see through the radio window. So I will spend a few slides to talk about radio astronomy and how everything started and what kind of processes cause this radio emission that we see in the radio sky. And then I will move on these high energy events that they called radio transients, and we will see what kind of types of radio transients we have. And in particular, I will focus on two types of those objects, the so-called X-ray binaries and gamma ray bursts. Then the reason is, first of all, we don't have much time, and second, because those are the type of objects that I've been working for the last 1.5 years. And if we have time, I will show you a little bit of results, what we can do with deep surveys with new facilities, and especially with SKA square kilometer array precursors, such as the one of MeerKAT. So let me start with exploring a little bit of the radio window. This is the spectrum. As we may know, as we all know, that the electromagnetic radiation comes in a wide range of waves, from shorter waves, the gamma rays here, all the way to longer waves, which are the radio in the red here. As we see, the narrow range of the optical and the radio window are the ones that are not being blocked by the atmosphere, and they arrive all the way down to us, to our telescopes. And the advantage of the radio is that it's a little bit wider than the optical, which gives a potential for unique discoveries of the universe. But unfortunately, this radio window has been a little bit silent, dormant field for a long time. So it's a pretty relatively recently, not like gravitational waves, for example, field, but it's not also that old as the optical astronomy. So everything started back in 1933, thanks to this legend guy who called Karl Jansky. Jansky was a radio engineer working actually for the Bell laboratories, the telephone laboratories, And he was at that time, he was assigned to look for some kind of interference, some kind of noise that can disturb the voice transmissions. So for this reason, he built an antenna, the one that we see here in the picture. It was an antenna that could rotate. So it took the merry-go-round name, so I could observe in different directions, operating at 20.5 megahertz, around 14.5 meters. And with this antenna, Jansky was observing for different directions for some months, and he identified it in principle three types of, as he classified, three types of noise. One was in principle thunderstorms, nearby and far thunderstorms. He detected also the sun, but the interesting thing that he detected, interesting for astronomy, was a repeatable signal at it had a period of 23 hours and 56 minutes. And this, not being an astronomer, signal is the period of a sidereal day, but not being an astronomer for him was a little bit hard to identify it. So he didn't find support, unfortunately, from astronomers, but looking himself on optical sky maps, he managed to publish his results and figure out that this kind of signal is coming from the Milky Way and is getting even stronger to the direction of the Sagittarius constellation. And as I said, he didn't find any support. It was also hard for him to continue, not being an astronomer. And the only person after this who got fascinated about Jansky's result, we'll come to a minute why astronomers were not interested at this point. So this guy, Grote Reber, in 1937, was fascinated by Jansky's results, and he built on his own backyard a radio antenna, a dish, a parabolic dish. It was a little more advanced than the antenna that Jansky built. And he was the one that actually, this dish had a diameter of 9 meters. And it was the first, he managed to do a survey in the sky. Also being able to observe in different directions. So he performed the first radio sky survey ever. And observing for several months in different directions, he managed to publish his results in APJ in 1944, where he showed the first contour maps of the radio sky, where also he showed the Cygnus A, one of the brightest radio sources in the sky, and also the supernova remnant, CAS A. But still, even during this time, astronomers did not show an interest, and they didn't show a lot of support. And the reason for this, it was because there was no mechanism that could explain the radio emission, the radio signals coming from the sky. At this time, Reber was uncovering a mystery uncovering actually high energy astrophysics that it was not explained till 1950s. And the reason for this is simply because astronomers, even till this period, the 1950s, had in mind that the main source, the theory was that the source, the main emission, the main radiation that comes from the sky is thermal, and in particular black body emission. So this kind of radiation that depends only in the temperature of the emitting object. So you have the perfect, the ideal absorber emitter. And since we have hot stars and hot bodies in the sky, so one would expect high energy light, would expect more high energy light than low energy. So the radio waves would be expected to emit around here, and then and hence nothing would be visible in radio. So that was the main theory till 1950s, and this was the main reason that both Jansky and Reber did not find any support for the astronomers, since they couldn't really explain this radio signal till the time that synchrotron emission, the non-thermal radiation, came into the game. Non-thermal radiation, synchrotron particularly, is the emission that comes from charged particles, electrons mainly, that are accelerated in by a magnetic field radially and produce radio waves. And as we go, as the longer the wavelength, the more emission is. This is the main mechanism that we meet in supernova remnants, in active galactic nuclei, and all compact jets, for example. Also, part of non-thermal radiation is pulsar emission. These emissions from objects with enormous brightness temperatures. And the radio astronomy was going like this till 1967 mainly, where the first beamed high energy source was discovered by Jocelyn Bell, the first pulsar. And yeah, as you see, for 30 years and more, the radio astronomy was kind of lethargic, I would say, was going pretty slow. Apparently, the radio sky is not static, it's not quiet at all. It has been dynamic. There are many events that are going on, extreme astrophysical events with high energies that we can study. And in particular, today we will talk about those events that are called radio transients and variables. In principle, everything that is on the radio sky that can vary, show pulses, it can burst, appear and disappear. So the main mechanisms for this kind of events are explosions that we see them in events such as gamma ray bursts, that we will talk about this also in a few slides. Supernovae, objects that they show accretion processes, mainly neutron stars and black holes. We see propagation in all scattering events. We see activity from stellar activity, flare stars, also variability from planets. And we have also other events, as they call the unknown knowns, that we still try to figure out what kind of mechanism is behind them. So the radio window has a lot of advantages, complementary to other wavelengths, of course. So we have, we can study those kind of explosive events that they result in particle acceleration. Those particles are distributed into the medium through accretion flows and relativistic jets. And this radio emission can tell us a lot about the kinetic energy. So we can constrain the minimum of kinetic power that we can see in those events. Also study a lot about the properties of the intergalactic and interstellar medium because of the radio wave scattering. And of course gives us also an excellent localization of the objects, especially with the wide fields and the sensitivity that the new facilities are having. So in principle, radio transients in the community, you will find people speaking about two main categories, fast and slow radio transients. Fast and slow in terms of the time that they evolve. So we have the fast radio transients that they show coherent emission. Usually we observe them in lower frequencies, and they are fast because they evolve in less than a second. So they are in millisecond scale. And we usually observe them using typical pulsar methods, time series analysis. This is a dynamic spectrum here. And this kind of objects can be, for example, fast radio bursts or rats, as an example. Also, on the other hand, we have the slow transients that evolve a little bit slower in scales from more than a second till years or even more. Those are show incoherent emissions. Usually we observe them, we study them through the imaging plane, not on the time series analysis. I mean, those kind of objects can be also detected in the image plane sometimes, but this depends on the sensitivity of an instrument of the time resolution. So those are the two types of transients that we have. In particular, my work is focused on slow radio transients. I'm studying those kind of objects in the imaging domain using radio telescopes. Those kind of objects, those kind of transients include sources such as X-ray binaries that are usually double systems, having at the center either a black hole or a neutron star, together with a companion low mass star. Intermediate mass black holes, those seeds as they thought to be of supermassive black holes. The ultraluminous X-ray sources emitting in Eddington luminosities, supermassive black holes at the center of massive galaxies, active galactic nuclei, tidal disruption events where the star reaches a supermassive black hole and pulls apart and happening this kind of spaghettation event. Gamma ray bursts, the most explosive energetic phenomena that we have been observing, supernovae, dwarf novae, and different stellar activities. And of course, the mystery transients. Today, as I said, I will say a little bit more about X-ray binaries and gamma ray bursts, since I've been working for those sources the last year or so. So let me start, please, with the X-ray binaries. X-ray binaries are systems, actually, are binary systems having in the center a black hole or a neutron star. I will talk about black holes in this part, and accompanied by a star, a companion, a low mass star that is called companion, feeding the central object by an accretion disk and interacting with the environment through outflows and jets that emit in radio. So usually those binary systems stay in a very quiet state for a long time, but every now and then they go into outbursts, and then all astronomers run to observe them because they're super interesting. The fact that we can observe those kind of objects in time scale, in a lifetime time scale, is very important, because those kind of objects seem to have the same physics. The physics underlying seems to be pretty similar with supermassive black holes. So it would be very important to, it's a great chance to study those objects, so it can give us ideas in order to proceed with physics that happens in more massive black holes, in order to study all those accretion and ejection physics at all mass scales. Because whenever you have an accretion, you always have an ejection. So what's more interesting than this? X-ray binaries, as I said, usually they stay in low luminosity, low accretion rates usually, but every now and then they go in outbursts. And this is actually the main evolution that they follow during the outburst. Here is the unified model of X-ray binaries, having the X-ray luminosity over the accretion in the y-axis, while we have the spectral hardness on the x-axis. In principle, the soft spectrum shows thermal emission, while the hard is more non-thermal emission. So after being in quiescence for some time, an X-ray binary will go into outburst. That always depends on the object, on the period will depend on the object. And then the X-ray luminosity will start to get higher and higher, even reaching Eddington luminosities. And this state is called hard state, where we have usually the presence of the jets. We can see the jets emit in the radio, and in this state, the thin plasma dominates from while it moves all the way to the left in the diagram, the thermal emission now comes from the accretion disk, and we don't see compact jets usually anymore. And then it will, the X-ray luminosity will go down, and it will move again back to the hard state, from the soft to the hard state, to go all the way to the quiescence. While it's moving from the soft to the hard state, we see in radio a lot of powerful ejection events. Usually we detect radio flares, and the jets can travel, we can detect jets at high distance, even kiloparsec scales, that are very interesting to study the feedback with a medium. Okay, so how do I study them? I use one of the square kilometer array precursors, the so-called MeerKAT. MeerKAT is one of the, actually is the most sensitive radio telescope that we have today. It consists of 64 dishes that each one has a diameter of 13.5 meters. They spread over 8 kilometers in Karoo Desert in South Africa. And more antennas, the plus 20 here means that more antennas are planned to be installed in the next year, increasing the baseline, the sensitivity in principle will be, the baseline will be over 9 kilometers. The operating bands now is currently is at L band, and in the commissioning state of lower bands. So this is mainly around 1.3 gigahertz. And also an S-band receiver is going to be installed soon. Typical resolution at this frequency is 6 arcseconds, and it operates with 32,000 individual independent frequency channels with full polarization, of course. How I'm using this instrument? I'm using this instrument through the ThunderKAT collaboration. ThunderKAT stands for the Hunt for Dynamic and Explosive Radio Transients with MeerKAT. This is one of the, I think, out of 10th large survey projects that have been given time with MeerKAT. ThunderKAT has been dedicated for almost 3,000 hours for 5 years in total. And the goal of this project is to study accretion and outflow processes in different type of objects, in mainly X-ray binaries, and that include black holes, neutron stars, white and white dwarf binaries. Also explosive phenomena such as gamma ray bursts, supernovae, and all the radio transients, fast and coherent, that fast radio transients that can be studied in the image domain. Particularly, I'm working on a key source that is called GX339-4. I'm leading a campaign for this. This is a galactic X-ray binary, being in around, the distance has not been constrained very well, but it's supposed to be around 8 to 12 kiloparsec. It has a low mass companion star, B-type, it's around 1 solar masses, and the black hole at the center estimated to be more than 6 solar masses, 5.8 solar masses, with a 42 hours orbital period. So I'm studying this interesting source, first of all, because this is one of the key sources that has shown us that there is a correlation between the accretion and the compact jets. So in principle, we have the so-called fundamental plane of black hole activity, where we have the radio flux density on the y-axis and the X-ray flux on the x-axis. And monitoring this source simultaneously in these two wavelengths and measuring the flux, it has been shown that there is a very tight correlation between X-rays and radio flux, which means actually that there is a relation between the accretion processes and the start of launching jets. So this kind of observations can help us to constrain models of the accretion efficiency, whether source is accretion efficient or inefficient. And this kind of source was one of the first showing this kind of relation that is also not only for stellar masses, stellar mass black holes, but seems to extend to supermassive black holes as well. So, and hence it's a key source that we can learn a lot out of this source. Of course, in this diagram, there are other sources that they called kind of outliers. They don't follow exactly the same track. And they also, they supposed to be explained with a different kind of accretion ejection model, but we will not talk about them right now. So, oops, yes. So I said this source is monitored by MeerKAT in a weekly basis. In principle, every week we turn the telescope into the direction of GX, taking an image of, taking an observation of 10 minutes and observe the variability of the source. Here I'm showing actually snaps of weekly images. It's a video of every week of the observations that we have so far, starting back on 2018 and coming even to last week. As you see, the GX339-4 is on the center of this figure, and it started from being completely quiet in the beginning and going back actually now in the quiescent state. And then it gives us it went to outburst. We observed radio flares. We observed the entire cycle from outburst to quiescence back. And this source is gonna, we're not gonna stop now here with this source. We're gonna monitor this weekly for the next 5 years. So as you may understand, having this kind of light years, this kind of data, it will be super helpful to have this coverage of multiple phases of the and events of the source, so it can help us to constrain all these accretion disk and Z models that are coupling. Okay, so for example, one of the exciting results that we published at the beginning of this year was using the sensitivity, thanks to the sensitivity of MeerKAT and X-ray satellites, we were able to detect this source for first time, have clear detection. There were thoughts and hints before, but it was not, we were lacking of sensitivity. So we were not able to confirm this kind of hint. That this kind of fundamental plane activity, this kind of correlation between radio and X-ray remains unbreakable all the way to low accretion rates when the black holes are going into quiescent. So thanks to MeerKAT, we managed to detect this source during this state, and we were able to place place this kind of activity in this diagram and make sure and confirm that this kind of relation remains unbreakable. And this is this is important, of course, because we're lacking of this kind of observations of quiescent black holes, and we don't really know what's going on, what is the physical interpretation when we reach these low accretion modes. Okay, so now I'm gonna move from X-ray binaries to gamma ray bursts. That's a very new topic to me, but it's pretty exciting. Gamma ray bursts. Here is the main, I'm showing you the main model, the main idea that we have of a gamma ray burst, the most explosive events, high energetic events. Usually gamma ray bursts are classified into long gamma ray bursts, GRBs, that are mainly come from a core collapse of a massive star, or short GRBs, or depending on the classifying them in terms of the duration, that they come from mergers of neutron stars or neutron star black hole, and the main, which actually are the main counterparts for gravitational waves. So there is the central engine here of that goes into burst. There is a bump, and then immediately we see this kind of prompt emission that lasts less than a second, And this is a lot of material that is going through the medium, and when it starts actually interacting with the medium, this large jet interacts with the medium, then we have the so-called afterglow emission, which there is a non-thermal process in the afterglow emission. It can last up to years, and is visible from all the wavelengths. But in particularly, I'm chasing this kind of objects with radio, because before I go to this and show you a recent result, I'm going to tell you why the afterglow emission is important. First of all, when the first GRB was explored back in 1967, if I'm correct, actually that was a detection. The first GRB was detected for information from the VELA satellites, from the satellites that the United States launched in order to see if the Soviet Union performs any nuclear weapon tests, since they had a treaty at this time, so US was suspicious. And during that time, with those satellites that were made to detect nuclear weapons, the first gamma ray burst was detected. But even 30 years after, after 30 years, it was the first time actually that the afterglow emission was detected. So we didn't have this kind of view of picture of the GRB. And this is very important now, because having an idea of the prompt emission and the afterglow emission as well, we can find out information about the mechanism, the central engine, and how efficient is the central engine, and what causes these objects to go into bursts. And yeah, since this is a non-thermal synchrotron emission, we can study the jet and the medium properties. It gives us a lot of information about the interaction, the feedback of what kind of energy, how much energy is released into the medium. So far, till the end of last year, actually, beginning of 2020, end of 2019, those kind of afterglow emission detections were limited in terms of spectrum. We were detecting them, a few of them, radio to up to giga eV emissions, but it was never detected in higher than this. And this is pretty important, because it helps us to understand how this, we were always curious to understand how these photons, high energetic photons that arrive to us, how they are created, what are the parental particles for this. So having detections more than high energy photons, detecting high energy photons helps us to constrain the models and have a clear idea of the whole spectral energy distribution. So as I said, in particular, I'm doing this part of from the radio observations that help us, as I mentioned before, to understand the kinetic energy, see where the peak frequency is, constraining the synchrotron self-absorption, and also studying the jet break. So I studied in particular last year, as I said, one GRB that is called 19011-4C, stands actually that it was discovered on 2019, January 14th. And this discovery was done by the satellites of Swift and Fermi missions. And they detected the signal of 10 to the minus 8 ergs per square centimeter per second. And immediately a multi-wavelength campaign started, because the signal was enormous. MeerKAT, of course, but also the main telescope for gamma ray detections, the MAGIC telescopes. It stands for Major Atmospheric Gamma Imaging Aircraft Telescopes. Immediately at 50 seconds after, Swift and Fermi detected this signal. MAGIC was able to detect the same signal at more than 20 sigma. So it was a clear detection. It was not an instrumental effect. And in the meantime, a lot of telescopes starting following up. So our side, I was doing the radio observations with the MeerKAT radio telescope. And we also, a few hours, if I remember correct, that was almost 5 hours after the first signal, we started observing it, following up with MeerKAT at low frequency at 1.3 gigahertz, also following it up with other radio facilities, such as the compact array in Australia. And we see that we followed this up to almost a year after to see how this burst, how this gamma ray burst will vary. And here in the center is this kind of source. As you see, it goes on and off. Of course, since we don't have a perfect resolution here, this emission that we see in the radio, it's not only coming from the GRB itself, but also from the host galaxy. So it's a mixture of emission. And as we can see here, that this kind of low frequency observations with MeerKAT and also the low band of compact array, the blue thing here, helped us to constrain the synchronous self-absorption that happens into less than 1 gigahertz. And yeah, it seems that the steep spectrum here at the higher frequencies, it seems to move. Yeah, that was one of the helping thing that MeerKAT provided, the radio observations provided in the multi-wavelength campaign that ended up to be very important, because that was the first time that we detected in this kind of energies, in tera-eV energies, a gamma ray burst. And having this in this plot here, I'm showing the broad spectral energy distribution, flux, and on the y-axis frequency, on the x-axis, the spectrum on the x-axis, in a different days after the first, in the different time scales after the burst. That's what the colors are shown for here. And having it's pretty, the lower frequencies at the beginning, the early radio emission, as I say here, is dominated by this back propagation, by the reverse shock, as I showed in the model. And yes, this was one of the main outputs. This kind of study ended up in a Nature publication, and it was worthy of, why was worthy of a Nature publication? First of all, because it was the first time seeing such high energy, such high photons coming from these objects. And second, because it helped us to understand from what is the responsible mechanism for those kind of high energy photons, which apparently seems to be the inverse Compton emission, scatterings of low energy photons to high energies. And in particular here, the X-ray photons scattered of the GRBs jet, this jet of electrons moving almost at speed light. And those energy of the relativistic electrons is transferred to the photons that come all the way to us. Yes, so now I'm leaving the gamma ray burst, and I'm going to talk about those mystery objects. For the GX339-4 field, which is this variable source in the center. As you see, this is an image. This image is not in optical, but this image is made by radio telescope by MeerKAT. This has 1 square degree here, the size of this image. As you see, we can see different kind of structures. Mainly every spot here is a radio galaxy. And also we can study objects that we didn't really know before, and we don't know how they behave. So we can study their variability. because, as I said, we have weekly monitoring, so we can have a very good time coverage to search about variability events in this kind of field. And with a very good sensitivity, reaching down to, this was an example of stacking all together 80 different epochs of 80 snaps of 10 minutes, around 13 hours in total, let's say integration time, resulting in 4 micro Jansky RMS. And that's actually doing this kind of studies help us. We found the first MeerKAT, the first transient with MeerKAT ever. This study was led by a PhD student from Manchester, where she searched for variability in the field and found out this guy here that actually is has a pretty low flux density, and without this kind of sensitivity, we wouldn't be able to see. This kind of transient, the first transient discovered by MeerKAT, that's why given the name MKT, was also detected in X-rays and shows also some UV emission, but it's really mystery. It's still, we don't really know the nature of this source. It seems to be a binary system spectroscopically, coincides the position with a K-type subgiant Tycho-star. Doesn't show any emission lines, so we keep going monitoring this thing till we find out what is the nature. So this is one of the excitements that triggers us to go more in observation. So I'm leaving this kind of studies can be done with MeerKAT, but not only. There are other surveys that they try to constrain this kind of rates, like in what kind of rates we can find those objects and what type of objects are. And that is apart doing it with MeerKAT, there are other telescopes that we can go deep, having different instrumentation capabilities. For example, the VLA, the Very Large Array in the United States. And using this kind of telescope as a part of CHILES project, we were looking for transients as well. I have this slide here as an introductory to understand what this project is. CHILES was a project that assigned for 1,000 hours in total, time of the VLA, of the Very Large Array, centered in the cosmos field, the field that is visited enough. So that means complementary data from other wavelengths exist to help us understand the radio objects that we find. The main goal of this project was to study H1 emission in high redshift galaxies, but on top of this, we are able to follow up to take observations in the continuum, so we can have images of 1,000 hours of observations and search for transient and variable objects in the sky. So for all kinds of explosions, collision, disruptions, the so-called name CHILES VERDES, which stands for Variables Explosive Radiodynamic Evolution Survey. And since this project is full polarization, we have also the continuum full polarization survey that is called CHILES Conpol. So I'm working in particular for the CHILES VERDES using the VLA. As I said, it's always in B configuration for having a specific resolution, 1,000 hours. That was observations taken back from 2013 to 2019. A lot of data every semester where B configuration, where a VLA was in B configuration, having a 0.25 square degree in a field of view with roughly 5 arc seconds resolution. So this is a study that just came out actually. I'm sorry. This is a very exciting results, data collected, all those data collected for all those years, having altogether searched for separate epochs, separate days of 172 epochs, finding in total, this is the field of the VLA. This is the field that we observed through the Chiles survey. So we detected there almost 370 sources. Those sources show, some of them, 60 almost sources show variability. Some of them show intermediate variability, some they show low. But we find variability up to 30% in this kind of sub-Jansky scale, because having 30,000 hours of observations, we reach a very good sensitivity, a very deep study. But also the different color noted for the different color, for the different variability state. Please check it out, just came out in the archive. So it's a very interesting study that helps us not only to constrain rates that we can find in this kind of blind surveys, but also see another important thing is like having our tools ready to search for, to do this kind of commensal searches with future facilities that are coming, for example, with square kilometer array. Okay, so not only variables were found, also flare stars that are popping on and off again, going on and off with different kind of light curves. It seems that we find more flare stars than what we expected in the beginning, and this is actually a plot that shows the expected rates of transients, what kind of objects also you can find in a certain aerial sky. Yes, aerial sky. The number of transients per sky area here, while the flux density, and all the things here note past surveys. Some of them, they went deeper, some of them, they went wider. Wider goes to the down, deeper goes to the left of the diagram, although this diagram seems a little bit complicated, but it's not. The point is to understand, actually to place rates, how many, what kind of expectation we have when we turn the telescope in a certain area of the sky and we keep observing this area for some time. What are the possibilities to find a certain type of an object? So with the gray lights here, here are the neutron star mergers, for example, tidal disruptions events, gamma ray bursts, active stars, and supernovae. It seems that flare stars are dominating. And the particular thing with Chiles Verdes is that this is one of the deepest limits that we have so far as a survey. So it's the deepest survey ever. Okay. Of course, this is not the end, but I would say this is the beginning of this kind of surveys and radio astronomy. For example, SKA is coming relatively soon. The square kilometer array, which will have a unique sensitivity and a wide field of view, will enable us to study this kind of objects, having new discovery, which means we will be it will be helpful to understand or explore new physics, new in those kind of high energetic events. In the picture, I saw the low and the low frequency antennas arrays for SKA. This is an artistic view and the offices of SKA, while here I'm showing the limits that are predicted with SKA, low and the deepest one here, where if you remember this, in this plot would correspond somewhere here. So I hope I convinced you that the radio and the radio sky, the transient and the variable radio sky is exciting. Extreme conditions can be studied there. Crash, especially, it's highly motivated for me to see when you always have, when you have an accretion, you always have an injection. So it's pretty exotic systems can be studied in violent conditions with high pressure, environment. And yeah, I hope in the future we will understand better, we will have a better understanding of the physics underlying behind those systems. So please stay tuned because the radio future is bright. Thank you very much. I hope I didn't take much time.
Thank you very much, Lilia. That was perfect. Questions, anybody? You can just unmute your microphones and speak.
I have a comment, Nikos Chilafis.
Okay. Hi.
Hello. You probably know that our group here is also interested in this exotic source GX339-4.
Oh, really? I didn't know this.
Okay. Yes.
That's good news.
And we look at it at X-rays.
Okay.
We have modeled the X-ray spectrum and its time variability.
Mm-hmm.
And our model makes a prediction for you. The model predicts that at the beginning of the outburst in this Q diagram, the break frequency in the radio spectrum, that is this frequency, that's it, right? So on the right part, the so-called hard and hard intermediate state, quiescence and hard state, right? We predict that as the source goes up in this Q diagram from quiescence up, yes, the break frequency will be increasing. And as it goes down on the other part, on the left part, the break frequency in the radio spectrum will be decreasing. Now, the second has been confirmed. So now what needs to be done is when we predict that the source will go for its next outburst, to see if we can arrange with radio telescopes, because we need measurements in simultaneous measurements in different frequencies to find the break frequency. And see how it behaves with time. So
okay, that would be excellent. Yeah.
So next time next time that the source goes into outburst, and it does it every couple of years, it would be nice to see how the radio spectrum behaves. Not just the total flux, but the spectrum, in order to determine the break frequency.
Okay. This is well. The good part is that, as I said, monitoring this source with MeerKAT, giving us 32,000 independent frequency channels. So we can also have an estimate of the in-band of radio spectral index. Plus, we can also have other radio observations in order to constrain the spectral index in different states. So that would be extremely helpful, and I think it would be great to talk more about this, because I also have more stuff to show you. This, for example, source has been already monitored since the end of 2018, even when MeerKAT was not fully operational with 64 antenna. So we have past data as well. So we have covered already a cycle. So it may be worth it to have a look together.
Okay. All right. So I'll send you a message.
Excellent. Thank you very much.
Wonderful. Papers being written on the fly. Other questions? Any other questions?
Either it was too clear or too complicated.
It was very, very nice. So what are the time scales? Let me just ask the question that you know has become very difficult to answer. So for example,
time scales in terms of outburst?
No. I mean time scales of completion of future projects and installation of new instrumentation. I mean, I don't know. I know that we have gotten, for example, a big hit in terms of COVID. Is there anything like that? You know, is anything pushed back considerably?
Yeah, for example, okay, I'm not really involved in the organization stuff and all this administration processes, but for example, I know, for example, France is trying to be in the board of Square Kilometer Array to participate. And well, the plan is with a data center, but all this has been stopped at this process, although it seems to be positive and things are going well. News haven't been heard for almost since March. Since March supposed to be the last decision, and nothing has been heard. So things are going slowly. Either when it comes to administration mainly, but in terms of engineering part of construction, things are still going okay. Yeah. Time scales. Well, time scales in particular. Are you talking about something particular in terms of?
For example, SKA. I don't know what the time scale we're looking at right now.
Well, now it's just last September, I think, the final construction plan was approved. So I think the construction will start end of 2021. If I'm not mistaken, starting, I mean, having the first probably data sets beginning of 30, end of 2028, something like this, to be more realistic, if everything goes well. Yeah.
Fingers crossed.
Yeah.
Any other questions for Lilia?
Lilia, could you please go back to your first slide so that I can copy your email address?
Absolutely.
Okay, so Evangelia.
First dot, last name at Observatoire Paris, .fr.
At OBSVM. Okay, thank you.
Thank you.
Anything else for Lilia? Vasily?
No, actually, I just wanted to thank you for a very interesting talk. That's all. It's just it's a bit on the side of what I'm doing, but it was very nice. Thank you very much. It was
Thank you for listening. Thank you for having me here.